In this last lesson, we're going to talk about cylinders and cones and spheres, and we're going to discover then some of the special formulas related to them. We're going to talk about their surface areas, their lateral areas and total areas, as well as their volumes and how some of them can relate to one another, depending upon the measurement of the radii or various heights and so forth. You'll see a lot of similarities from the previous lesson when we compared prisms to pyramids. A cylinder is a prism-like solid figure, only now with circular bases instead of regular polygons as a base. A cone is a pyramid-like solid figure with a circular base, or it could have an elliptical base. We have a right cone looking like this. We can also have an oblique cone looking like this. The base of these may be circles, or they both could be ellipses. But again, this is a right circular cone, the way it's drawn, the base being a circle. This is an oblique circular cone. Again, if the bases were ellipses instead of circles, then this would be a right elliptical cone, and that would be an oblique elliptical cone. Now, let's talk about some of the parts of some of these figures. A part of a cylinder, we have, of course, the base, which would be this circle here, and then on the other side as well, equal circles in a circular cylinder, a right circular cylinder. We also have an altitude, which is the measurement from the very top to the very bottom, perpendicular to the base, of course, in a circular cylinder. And then we have the radius of the cylinder. The cross-section of this circular cylinder, of course, is a circle, so the radius of the cylinder would be the same as the radius of that cross-section that's a circle. Then we have its axis, which would be from the center of the top up here to the center of the bottom down here, in the case of a right circular cylinder. That's the axis of the cylinder that it could spin around. And then the lateral area, like the other solid figures, would be the area of this face around here. And also then the total area would be a matter of adding this lateral area to the top and the bottom. That would make the total area. The volume of this thing, of course, would be the amount that it contains on the inside. Like a pyramid or like a prism, it would work kind of the same way. In a cone, again, it can be right or oblique, as I mentioned. This is the vertex of the cone up here. This is the base. We'll call it the circle. And the slant height is the measurement along the edge here on the surface. That's the slant height. Now, the actual height of the cone is still officially, like always, perpendicular to the base. But now we have this side often used in some formulas, and that's called the letter L, slant height. S-L-A-N-T, height. So, be aware of this. In a cone, we have a height and also a slant height. There is, of course, a major difference. Okay? Then this is the axis of the cone. From the vertex of the cone down to the center is the axis of our circular cone. And again, we have the lateral area, which would be the area of the upper portion. And if you add on the area of that one circular base, that would provide then the total area. And of course, it does have volume too. And we're going to see how that volume would compare to the volume of a cylinder that it could be put inside of with the same height and the same base. How would the volume of that cone, you suppose, compare to the volume of the cylinder, given the same area of the base and given the same height? All right, let's look at our first formula here. The lateral area of a right circular cylinder equals the product of the circumference C of the base and the height of the cylinder. Now again, like in the prism and the pyramid, most of these formulas are very, very logical, the way they can evolve. The lateral area is equal to the circumference times the height. Well, the lateral area is just the area, around here on the face. If you sliced this and uncurled it, you would get a simple rectangle. Okay? So let me take this rectangle. The dimensions of a rectangle have a base times the height. That was the area for this rectangle, base times height. Now, if I take this rectangle and curl it into a circle like this and make a cylinder, then look what happens to that base. The base of the rectangle now becomes the circle around the cylinder. So that's the circumference right there. That replaces the base of the rectangle, see? So it's a very naturally logical, logically follows from the formula for the lateral area or the area of a rectangle. The height is still the same. The height of this rectangle is still the height of the cylinder when you curl it up. So again, it is a very logical type of formula. Let's plug in some numbers here. Let's say this radius of this base is 4 and the total height is 8. And see what kind of numbers we come up with. What would be the lateral area then? Just the area around the face here. Okay, the circumference of this circle is 2 pi r. So we can replace circumference with 2 pi r. And then times the height. Okay? Now, it's probably more logical for us to think of it like this and see how it directly evolves from the rectangle. But again, the circumference, you know, the circle is 2 pi r, and now we're ready to go. So 2 times pi times the radius of 4 times the height that's given here in this problem to be 8. So multiplying all that through, we would get 201.06 square inches. Okay? Again, we're talking about lateral area, so remember any kind of an area should have square units attached. How about the total area of a right circular cylinder? Now, we're going to deal mostly, of course, with the right circular cylinders as opposed to an oblique cylinder or an elliptical cylinder because they are much more common. An elliptical cylinder would be somewhat like a muffler shape. You know, the cross-section would be more like an ellipse. But again, you have a lot more in everyday life, a lot more right circular cylinders than anything else. So that's what we're going to specialize in today. The total area of a right circular cylinder equals the sum of the lateral area and the area of the two bases. Well, of course, very logical. The lateral area plus the area of any of the bases, and a cylinder has two of them, the very top and the very bottom. So logically, we have to add the lateral area to two circles. If you were to take this cylinder and slice it and uncurl it, here's what it would look like. You'd have a rectangle that would uncurl for the lateral area, and then the top and the bottom would be these circles like this. That's all it is. When you add on the circles, now you have a total of 3 areas, so that's total area. So this cylinder is simply made up of a rectangle and 2 circles. That's all it is. Okay? So that's how we can find total area. The volume of a cylinder equals the product of the area of the base and the height of the cylinder. Well, okay, there again, like the prism, compare this. It's the very same formula because it's the very same idea. To find the volume of this cylinder, find the area of the base, fill it in the circular region, the area of the base, and that times the height. You would lift it right up through the cylinder just like an elevator going up through the shaft. It would just fill it right up. So that would give us the volume of this thing. Let's work some numbers into that to see if we can use that formula. Volume is the area of the base with a capital B. Now notice that capital B does stand for the area of the base. Small letter b could be like the base of a trapezoid or a triangle or a rectangle parallelogram, but capital B means a two-dimensional thing. It means, more importantly, the area of the base. All right, so let's say we have some numbers here. Let's say this radius of this thing is 4 again, and the height is 8. Same cylinder we had over here. So the volume would be, the area of the base is pi r squared, and then times the height. So if you see this formula here, that might look kind of sophisticated and a little scarier for you, but when you think of it in terms of the area of the base times the height and break it down that way, and then substitute. Well, what is the area of this base? Is it a hexagon? Is it a square? What area formula would I use? Well, no, it's a circle this time, so what's the area of a circle? So you substitute that in for the base. All right, so r squared would be 4 squared times the height, which would be 8. Now, remember your order of operations here. Before you can multiply anything, you must simplify the power of 2 there. So you have 4 times 16 times 8. And when you finally multiply it all through, you'll get 402.12 cubic inches. Recall we're talking about volume now, so we're talking about inches times inches times inches. So we have cubic inches for volume, or cubic units of any type. The lateral area of a right circular cone. Now we go to the cone. The lateral area having a slant height L. See, we're going to use the slant height now. And the circumference C, which is 2 pi times the radius, where r is the radius of the base, is 1/2 the product of the circumference and the slant height. Okay. The lateral area then is 1/2 the circumference of the base of the cone times the slanted height. So then we get that condensed formula there down at the bottom of pi RL. All right, let's take a cone like this, a right circular cone, and give it some dimensions. Let's make this 4 and make this 8. Okay? We've got to find the slant height before we can go on to find the lateral area. If you write down the formula, lateral area equals 1/2 the circumference of the base times the slanted height. You see, when this started out as a cylinder, like we had a little bit ago with these same dimensions, we had one lateral area, which would be the circumference of this times the height. Now it's tapered into a point, so it's the circumference of the base times 1/2, and that height now becomes into the slanted height. So it's kind of a related formula from the lateral area of a cylinder. So this is 1/2, again, the circumference is 2 pi r times the slanted height. Okay, we're stuck here, though, until we can find what L is. We need to find the slanted height of this. Well, looking at this as a right triangle, we'd have to use the Pythagorean theorem. The Pythagorean theorem bails us out in many problems to help us find the missing side in a right triangle. So 4 squared plus 8 squared equals L squared. So this is 16 plus 64, or 80, equals L squared. Therefore, L equals 4 radical 5 exactly in radical form, or approximately 8.94 as a decimal. Okay, so we plug that in now over here, and we can continue on. 1/2 2 pi times the radius of 4 times the slanted height L now of 8.94. Okay, now it would be a little bit more accurate if we did use the more exact number, 4 radical 5 in here. If we round off to a certain decimal, then we're going to have a rounded off answer more magnified at the end. So just be cautious about that. So now, multiplying all this through, we would have the lateral area to be 112.4 square inches. Okay, 112.4 square inches. That's the lateral area. If we wanted to take total area of this cone, what do you suppose it would be? Logically, yes, the lateral area plus the area of this base. That's the next theorem. I bet. Oh, it sure is. The total area of a right circular cone is the sum of the lateral area and the area of the base, just as we logically figured out. So now, how are we going to figure that out? We know the lateral area now is pi RL, or 1/2 the circumference times the slant height L. Now all we have to do is add on the area of the base. Well, the area of that base is the area of a circle, pi r squared. So the radius is 4. So we have pi times 4 squared, or 16 pi, which is approximately, as a decimal, all together. Okay, we'll take on 16 pi, and that's the area of the base. So now we want total area. Get it all together here. Lateral area plus the area of one base. Lateral area we already computed to be 112.4 square inches. And now we add on the area of that base, which is 16 pi. And when you multiply all that out, 16 times pi, and then add it to 112.4, you'll get 162.67. That's for the total area. And again, now that you know what total area is, you can just logically figure it out. You've got to find the area of the surface around this way, the lateral area, and then just add on the area of the circle for the base. That's all there is to it. The volume of a cone is given by this formula. It's the very same formula as the volume of a pyramid. The volume of a pyramid. You know, a cone is like a pyramid, only it has a circular base instead of a regular polygon type base. The volume of a cone is 1/3 the product of the area of the base and the height. Okay? So that's 1/3 pi r squared, the area of the base, pi r squared, times the height. Let's find the volume of this same cone right here. The volume of this cone, as given here, would be 1/3 the area of the base times the height. And again, that's like the pyramid compared to the cylinder. Or the pyramid compared to the prism, mixing all these solid figures up. The pyramid that fits down inside the prism was 1/3 the volume of the prism. Now, by comparison, the volume of this cone, we find, is 1/3 the volume of the whole cylinder. It works the same way. Because the cylinder has this area right here, area of the base times height. But the cone is 1/3 of that. So here we go. The area of the base is pi r squared times the height. So it's 1/3 of that. So plugging our numbers now, we have r, which is 4, so it'll be 4 squared. The height is 8, and now we're ready to multiply through. So it's just a plug and chug formula. 1/3 times pi times 4 squared. We have to simplify the power first of all, remember, and we get our volume finally to be 134.04 inches, square inches. No, this is volume, so it's cubic inches. Okay, assuming this was inches to start with. All right, let's compare now the cylinder and the cone values and formulas. The lateral area, total area, and the volumes, comparing the cylinders to the cones. Look how they do compare. The lateral area of a cylinder compared to that of a cone is very closely related. Circumference times the height for the cylinder. For the cone, it's 1/2 the slant height. When you taper it into a point, it's 1/2 of that height slanted over. It goes still with it, times the circumference of the base. Okay, so that's how the cylinder surface area, lateral area, compares to the cone. The total area is the lateral area plus 2 bases, because that's what the cylinder has, the top and the bottom. The cone, by contrast, is its lateral area plus 1 base, 1 circle, pi r squared. And here again is the comparison I wanted to show you, like the pyramid inside the prism. The cone inside the cylinder would be 1/3 of that volume. So the volume of this cone in here would be 1/3 the volume of the entire cylinder. Okay? Let's go and let's talk about a sphere here a minute. The area of a sphere of a radius r is 4 times the area of a great circle. But what's so great about a circle? Well, it's so perfect. It is always equidistant from a fixed point called the center, and it is perfectly shaped. Very difficult to make a circle. You know, the easiest way to do it is to just take your arm like this and get it swinging and make your circle around that way. If you want to draw 2 circles, you get both arms going and draw them around this way. You get a perfect circle every time. But that's what's so great about a circle, because they are perfect, all of them. The area of a sphere is 4 pi r squared. Okay? It can be shown through a rather sophisticated derivation, actually, more than we have time for right here. So if we have a sphere with a radius of 5, draw our axes across here like so. Imagine that being a 3-dimensional sphere, radius of 5. What would be the area of this, total surface area, and also then we're going to find out what the volume of it would be as well. So, the surface area of the sphere is given by the formula 4 pi r squared. So it'll be 4 times pi times 5 squared, which is 4 pi times 25, which would be exactly 100 pi if you were to leave it in terms of pi, or 314.16 to the nearest hundredth if you wrote it out to the nearest hundredth of a square inch. Now, why is it 4 times the area of a circle? The great circle of a sphere would be the biggest circle that you could slice by going through the center of the sphere. I could also slice the sphere, up in here like this, or up in here closer to the top like this, and I get smaller and smaller and smaller circles. And same thing on down in here. But the great circle is a circle that goes through the middle or the center of the sphere. So why is the surface area, do you think, 4 times the area of just one circle? Well, it can be shown here by some sophisticated methods that the area of this great circle is actually the same as this area of this sphere surface right in here. If you can imagine this divided into 4 quadrants, you might say, by this vertical plane and the horizontal plane, this surface area of this figure in here would be the same measure as a great circle. The volume of the sphere is given by 4/3 pi r cubed. The volume of a sphere with a radius r is 4/3 pi r cubed. Let's see how the volume of this thing would compute out then. So the volume is 4/3 pi r cubed. Okay, again, this radius is 5, so it's 4/3 times pi times 5 to the 3rd power, or 5 cubed. And again, remember, you must cube the 5 before you can begin to multiply across there. So multiplying that on out for the volume, we would get totally 523.6. And again, remember, it's volume, so it must be cubic inches. You had 5 inches to the 3rd power, so that's inches times inches times inches, or cubic inches. 523.6 cubic inches for the volume of this sphere. Now, let's compare the volumes of spheres according to the radii. Here is something that we saw back in chapter 17 to start with, comparing the corresponding parts of similar triangles. We saw it again when we got into similar polygons besides similar triangles, and now we can expand it to the volumes, because now we're into 3-dimensional figures here. Here we have the corresponding ratios of the perimeters, circumferences being the same as, corresponding linear measures of any part. The ratio of the base areas or lateral areas or total areas are a squared to b squared, using the square of the scale factor a to b. And now, here's our last extension of this. The ratio of volumes would be a cubed to b cubed. Let's see how that would work. What do we mean by that? Well, let's take 2 spheres with different radii and see how their volumes compare to their radii. Let's say we have a sphere of a radius of 5 compared to a sphere with a radius of 10. Okay, how do these volumes compare? Well, the volume of this is 4/3 pi r cubed. So that would be 4/3 pi times 5 to the 3rd power. And if you multiply that out, you'll get 523.6, as we just did. And now the volume of this over here would be 4/3 times pi times its r cubed. So that would be 4/3 pi times 10 to the 3rd power. So multiplying that out, 10 to the 3rd power would be 1,000 times pi times 4/3, and you get 4188.8. And again, of course, that's volume, so it's cubic inches. Now, compare these volumes one to another by comparison of the scale, the radii. The radii compared 5 to 10. That would be a linear measure, you see. A to B, or the linear measure, 5 to 10, which is the scale factor then of 1 to 2. But how does that compare to their volumes? The last conclusion now of this last theorem, 30-9. Well, if I divided the volume of that bigger sphere by the volume of the smaller sphere, it would divide in there exactly how many times? 8 times. That's right. Because 1/2 to the 3rd power would be 1 cubed to 2 cubed. So that would be 1 to 8. So in other words, if we knew the volume of a certain sphere, and we knew how the radii compared from one sphere to another, then the volumes would compare by 1 to 8. Okay? 1 to 8, that is, if their ratios of the radii are 1 to 2. If the radii were in a ratio of, let's say, 2 to 5, if we had two different spheres in a ratio of 2 to 5, then the ratio of their volumes would be 8 to 125. And then you can use that as a ratio and proportion to solve for a missing volume. All right, let's take our sphere of our Earth and a practical application. The radius of our Earth is a little bit less than 4,000 miles. The radius is 3,982 miles, the last time I measured it. And let's find out what the circumference of our Earth is. And also let's find out the lateral area. Okay, so this radius is now 3,982 miles from the center of the Earth out to a surface point. What is the circumference around here? Well, the circumference is 2 pi r. That would be around the distance here at the equator of this great circle. So that is 2 times pi times the radius of 3,982. And if you multiply all that through, you'll get 25,019.6 miles. That's the distance around the great circle of our Earth, around the equator. Around 25,000 miles and a little bit more. What would be the surface area? How many total square miles do you think would be on our Earth altogether? Well, that would be the lateral area, which is the same as the total area in the case of a sphere, and it is 4 pi r squared. So, plugging our numbers here, 4 times pi times r squared, where r is, again, 3,982 miles. And again, we have to square this first and then multiply it times 4 pi, and it'll come out with a big number of 199,256,444, and that is square miles. That's the total surface area of our Earth. And again, as I say, in a sphere, the lateral area is the same thing as total area. So the surface area of our Earth is almost 200 million square miles. 200 million square miles. Okay, we have one more major postulate. We're going to end up with a postulate. We started out with postulates, which gave us, statements that we can accept as being true with common sense, without any kind of a necessary proof. And now we're going to end up with a postulate. Cavalieri's principle says that if we have two solids of equal heights, and if the cross-sections formed by any plane parallel to the bases of both solids have equal areas, then the volumes of the solids must be equal as well. Now it says two solids. That could be prisms, pyramids, cylinders, cones, but they have to have equal heights and equal cross-sections. So if we have, let's say, a cylinder, like so, and a prism, like this, if they have the same height, and a plane slices through them so that the area of this cross-section where the plane slices through is the same as the area of this where that same plane slices through, if those areas are the same, if somehow we knew the area of this circle was the same as the area of this hexagon in this case, then the volumes of these must be equal as well. Kind of an interesting little principle here. So again, if the heights are the same, and if the cross-sections have the same area, then the volumes must be equal as well. That's if they're sliced by the same plane coming through here. Well, we've gone a long ways here from our first postulates, basic ideas of points, lines, and planes, and then extending that on into space. Then we added the points and lines and planes to angles, started making figures like triangles, polygons like rectangles, squares, rhombuses, trapezoids, kites, parallelograms, the list goes on, and then on into circles. We tried to develop some logical thinking process as we added the theorems and postulates along the way. We kept building our blocks, from our foundation up. And we finally built that house we talked about in the first lesson. We had to lay the groundwork first, and again, the more tools we accumulated, the easier it was to build that house. So I hope you've enjoyed this series, and I hope you've learned a lot. But again, remember, you have the luxury of going back and rewinding and helping yourself to the added necessary facts once again.